Okay, so hi everyone. My name is Nikhil Barthwal. I'm going to talk about how we implemented our event-driven microservices architecture in F#. I'm going to explain what that is, but before I start, I want to give a little bit of background on Jet.com. Okay, so we were launched in July 2015, and last September we were acquired by Walmart for $3 billion. I have some numbers here: 8 million customers, 25,000 orders per day, and 15 million items in the entry. The reason I have these numbers is I want to give you guys an idea of the scale at which we operate. The core crux of our product is a dynamic pricing engine. That is that when you shop, the system would basically look for all the ways in which it can reduce cost for you. So how it worked is when e-commerce started in 1998 or something like that, when Amazon started, right? E-commerce was priced around convenience, give you the most convenient way to shop. What we do is we innovate around price because we believe that e-commerce has entered into a mainstream market now. So at that time, the people would go to a place where we can get the cheapest goods possible. Okay, so moving on to the technology stack, we run on Microsoft Azure. That's kind of fairly obvious because when we started, Amazon was our core competitor, and you don't want to build, a competitor on his platform. So no AWS, please. .NET framework. We use a mix of technologies here: Kafka as our message bus, Redis for in-memory cache, Splunk for log management, event store for events, storing events. The bulk of our backend is actually in F#. There was a talk on F#, so I'm not going to try to explain what F# is, but just briefly, it actually takes the OCaml core and it adds the object-oriented layer for .NET. It runs on the .NET platform. Okay. So few things on architecture. We use domain-driven design to, I'm going to go into details of each one of them, but on high level, we use domain-driven design. So domain-driven design is a methodology that connects a software implementation to an evolvable model of the system. We use event-driven architecture. Event-driven architecture deals with production, consumption, and reaction of events. Event sourcing basically is a notion that system should don't store the state, but store the sequence of events that you can replay to get the state of the system. And there was a talk about microservices also. It was mentioned in the previous talk. So microservices are small, independent, granular services, and microservice architecture basically is instead of having one monolithic service, you have these small microservices that work together to give you the functionality. All right, domain-driven design. I don't want to go too much into domain-driven design, but it talks about ubiquitous languages as software developers can use it. It deals with models, and what happens is that for most complex systems, you can't have one model for everything. So it talks about what is called as a bounded context, which is basically set of interrelated models. So this is an example from one of the services called Thor. So they use, so you see bounded context, and there's an architecture pattern there called CQRS. CQRS stands for Command Query Responsibility Segregation. I know it's a scary name, but it's actually pretty simple. It says that every call should either give you, if it's giving you a response, should be a pure call. Or if it's modifying the change of it's changing the system, then it should not give you a return. So you could either have a response in a pure functional call, or you can modify the system and get no response. So that way you don't have basically what it does is it prevents you for getting a response and having a side effect at the same time. So that kind of gives more predictability through the system. Okay, so one of the common architectures for DDD, it's hexagonal architecture. Basically, there are 4 layers. So you have the presentation layer, right? There's a thin application layer shown on green. Bulk of your code is actually on the domain layer, and then finally you have the persistence layer, right? And it's called hexagonal because presentation and persistence actually are split into 2 parts. This is your actual production services, and these are your test stubs. Similarly, on that side, these are your test drivers, test stubs, and your actual persistent stuff. So the term domain-driven design was actually coined in 2003. There was a book by Eric Evans with the same name. And it got popular, and if you read the book, it's actually a big 500-page book. It tells you, it gives you an example of DDD, and it uses Java as the language for all the examples. But what turns out is functional languages tend to be very, very suitable to do it, to implement this kind of architecture. DDD talks about what you call as a value objects. And as you can see from the diagram, bulk of the code actually stays in the domain layer. And value objects are essentially immutable objects which have some methods attached to it that they won't transform the object itself, but they might generate new objects, right? And you can have this kind of functionality easily implemented in a functional language because A, you have immutability by default, right? And ADTs, in F# we have discriminated unions. I know in Haskell, OCaml, they have similar. Haskell has those data types, and OCaml has the same. Basically, ADTs are very, very suitable to model these kinds of domain objects. And there's a pattern in DDD called anemic domain model that generally should be avoided. And what anemic domain model is, that your value object should not just be a bunch of getters and setters, but they should actually have some functionality. As it turns out, in F#, you can attach member functions to these immutable objects, right? So you can even prevent anemic domain models from happening by attaching attached member functions. I don't think that's something available to OCaml or Haskell to my knowledge, but then I'm not an expert of OCaml or Haskell either. Okay, moving on, event-driven architecture. I briefly explained what event-driven architecture was, but going into more details, event occurs when there's a change in your system, right? So we'll go through some examples. And how it works is that there is a source that actually generates an event, and there are listeners that are listening to that event, right? And once the listener listens to that event, they might take some action based on what kind of event it is. And it's a very highly distributed loose couple architecture, right? The problem with such kind of architecture is the traceability of information is not there. A very common example of event-driven architecture is if you go to the airport, right? There's a person who makes an announcement that you have a flight leaving like 15, 20 minutes, right? That's an event. Something is going to happen. The passengers on the airport are listeners, right? Some of them may take some action, particularly ones that are going to board that flight. Others might choose to ignore it. And it's a highly distributed loose couple architecture in the sense that the source, the person who makes an announcement, he has no knowledge about who the listeners or the passengers are. He just makes an announcement, right? And it goes in like an either end, people may listen or ignore and so on. And the source has no knowledge about the listeners or what action they take. And that is why it's an asynchronous method of flow of information, right? And you can't really trace what happened after that. Okay, so closely related to event-driven architecture is event sourcing. In event sourcing, your state of the system, as I said, is stored as sequence of events. So every time there's a change happens, the event is generated, you store that event, and what it does is that if you don't have the state, but you have the individual sequence of event from start, you can roll back at a particular time and you can get the state of the system. Knowingly or unknowingly, all of us use event sourcing in one form or another. For example, your version control system is an event sourcing example, right? When you initialize a new Git repository, you have an empty repository there. And as you make commits, each commit is an event. And when you clone your repository, Git would just add up all the commits and give you one final state of the system, which is the state of your source code, right? And you can log and get a list of all the commits. And if you want to replay, if you want to get the state at a particular commit, you can actually clone that particular, you can check out that particular commit and you get the state of the system at that point of time, right? So it enables rolling back. Yeah, so that's one example of event sourcing. Your bank is also another example of event sourcing, right? You open up an account, and initially you have a balance 0, then every transaction you make is an event. So in old days, they used to have passbook. Right now, everything is digital. So you have the bank statement where each one of the transactions, which is essentially an event, is logged, and you get the final event as sum total of all the transactions. Now, one common question that comes in event sourcing is, isn't it slow? I mean, if each time I have to get the state of the system by replaying all the events, then seems like the system is dead slow. Well, yes, and there are practical ways in which you can mitigate this. For example, you have all sorts of ways in which what sometimes people do is the cache, right? So while you're storing the individual events, you might have a cache. Let's say I cache my system state at midnight. So if at 8 o'clock I want to know what my system state is, I would take the cache from 12, and then between 12 midnight to 8 a.m., I replay the events to get the state at 8 a.m., right? Banks do that in the sense that you also have your final account balance always with every transaction. So you're doing the caching with each transaction, right? I'll skip this one. Okay. So here's another example of event sourcing. So what you see here is, let's say this is like a social network, right? Simplified form of social network. And you have events that goes in your message bus, in this case Kafka, and you have different kind of application like monitoring cache that are reading these events. Now there's a very particular thing about event sourcing. What event sourcing does is you can have application that can process the same event but generate a different view, right? So here you have all these applications that are going through your event bus and consuming those events but generating different view. For example, if you think about Facebook, right? Your social network, right? If you look at Facebook, you have your timeline on the right side, you have your personal info section, you have a photo app, right? Think of them as 3 different applications. And then everything that you do, you post a message on the wall, post a photograph, put a life-changing event, something like that. These are all events. So let's say if I put a message on your profile, that's an event that gets logged in my timeline. The same event is received by the personal info section and photo service. They'll just ignore that. Then I post a new photo. The timeline puts the photo. The personal information section, again, ignores that, but the photo application picks up that event and adds that photo. So now you have that one event that is coming, that I'm posting a photograph, but it's being consumed by these 3 apps in a different way. Similarly, let's say you're single and then tomorrow you get married, you have the event coming, your personal section would get updated from single to married, your photo section remains the same. So again, the same event processed by 2 different applications generates 2 different views. Any questions so far? Okay. Moving on, microservices. Yeah. So before I go to microservices architecture, I just want to talk about what a microservice is. So microservices, as per the definition, are small autonomous services that work together. And what they do is they tend to do one thing and one thing really well. And there's a controversy about how small is small, because it's an empirical definition. So the rule of thumb is that if you can write or rewrite a service in 2 weeks, that's small enough, right? But then again, it's a very empirical definition, because if you have Haskell, then you might have more functionality in less amount of time and vice versa, right? So there's no hard and fast definition. But microservices follow single responsibility principle. What single responsibility principle says is there should be one and only one reason to change a service, right? So now we come to microservices architecture. Microservices architecture basically has all these small microservices that work together. The opposite of microservice architecture is a monolithic architecture. So you have one service that does everything, right? Each microservice runs in its own process, and it communicates with each other at lightweight mechanisms. Typically, these mechanisms tend to be like HTTP or REST calls, or it could be TCP calls also. We have about 1,000 microservices in production, and it's not too uncommon to have large number of services in a typical distributed system that uses microservice architecture. Okay, so what are the advantages of microservices? Why would we use them? The first advantage is we have the independent releasability, right? When you have one monolithic service and your entire organization, the code resides in one service, let's say if I make a change and I need to redeploy, I'm not just redeploying me or my team's change, I'm actually redeploying everything, including other teams, right? And that kind of creates a synchronization problem, and there's a coordination problem. Teams kind of don't work that way, right? Every team wants to have a control over its own code. Also, microservices tend to provide you a better scaling. What do I mean by that? Let's say I have a service and one part of it is heavily loaded, right? And I need to replicate it. Because let's say in a traditional monolithic architecture this happens, if you have to replicate the service, you would have to replicate the entire service. That's because monolithic service is treated as one unit. So as a result of it, 5% of your code is heavily utilized, 95% is not, but you would have to redeploy that 95% also, right? So that leads to a lot of resource wastage. So with this kind of architecture, what you can do is you can replicate only the service associated with that part and leave the rest as it is. So that way you get a much efficient utilization of your resources. You also have technology heterogeneity, which means in a monolithic architecture, if you're using a technology, Java or whatever, you have to implement the whole service in that language, right? Whereas in microservices, since they are communicating using a technology agnostic protocols, you actually can have one service and one technology, another service and another technology, and you can have like a bunch of them. There's also a major advantage of resilience, right? Let's say one part of your code, there's an exception and the service crashes. With monolithic, if there's an exception thrown, the entire service crashes, right? With microservice, that one particular service would crash, but your remaining 999, if you have 1,000 services in production, right, they work just fine. So there's a big deal of resilience built in the system. And finally, ease of migration, right? So let's say I want to migrate my service. In a monolithic architecture, when I migrate, I would have to redeploy the entire service all in one. So that's a big risk and a big change. Whereas when I have my system in form of, let's say, 1,000 different services, I can redeploy them part by part. So as a result of it, my granular unit of redeployment is small, and there's much less risk associated with migration. So this is an org structure. We name our teams as superheroes, right? So you have Batman, you have Profix, and I see a bunch of people here from my company. So I know Nikki is from Profix, and Gina is from Marvel, and then I'm from Forge, and we have 2 more people. I'm not going to go and explain each one of these teams, of course, but just to give you an idea, let's say, this is the front end, Profix is the search, this is the inventory, Superman is actually the pricing. So what you see here is basically how the data flows, right? And each one of these teams actually owns a bunch of services. So it's not just one service, right? You could have like 20 service here, 30 service there, and so on. So let's talk about deployment, right? There are 2 different ways you can deploy these services. So now what you could do is you could have a request response system, which is more like a synchronous system. So typically, one service would make a call, it expects a response, and so on. Pretty simple to implement, pretty simple to maintain. And then you have the event-driven, which is asynchronous. And in event-driven architecture, what happens is you have that message broker in between, right? So each service, they would throw an event, and they get back. Request response system tends to be more reliable. Event-driven system tends to be less reliable but more scalable, whereas request response is actually less scalable. And the reason why it is less scalable is, let's say I want to add a service here, right? I want to add a service that contacts this service, and these services have to interact. I have to add this code. I have to change all of these codes, right? Now imagine I have 1,000 such services running. So making a change is risky, right? And I could have changed several parts of the code. So that is why it's not very scalable. Whereas in an event-driven, right, you have the central message broker. So if I want to add one service, I just have to add another hook to that, so I can read and write events from the message broker. It's just easy. Those services, I don't even have to have a change. So that is why that is less scalable. But now, in this model, here's the problem. First, your message broker is your single point of failure. If this fails, your system goes down. Whereas here, if this fails, the rest of the services work very well. The second problem is that you don't have traceability, right? I send an event, I expect a response, I didn't get it, I don't know what happened. Whereas here, when I make a call to a service, either I get an answer back or I get some kind of error, right? The call failed, it won't be 400 or whatever. So there are both pros and cons for these patterns, and typically how we implement is we divide our services into 3 tiers, right? Tier 1, Tier 2, Tier 3. Tier 1 is something that if it goes down, it impacts the customer quite a lot, whereas Tier 2 is something that impacts the customer but not a lot. And Tier 3 is something where impact is practically not at all. For example, let's say the pricing. If the pricing service goes down, you can't use the site. You're done, right? Or if it goes down for 2 hours, for those 2 hours, the site is non-operational. If the order management goes down by 2 hours, you can still place the order, they just won't be processed. So your orders would be delayed by 2 hours, so it's an impact to the customer, but not a significant one. Whereas a monitoring service, right? If it goes down for 2 hours, you can't monitor, you can't log, but the customer is not impacted. How we generally tend to deploy is our Tier 1 services tend to be more on the request response pattern because these are more reliable, whereas Tier 2 and Tier 3 generally would use more on event-driven side. So that's a functional view of a microservice. A microservice can be thought of as a function that accepts an input and give you a response, right? Most of the services tend to be stateless. So most of these services, I'm going to call them pure services, which is basically pure functions, right? There are no side effects except for as logging. If you're just logging it to a text file or somewhere, that's OK, although it's a side effect, but it doesn't really impede in any way. Now, there would be some services that interact with the persistence layer, right? For example, they'll have some storage attached to it. So there, you have a state of the system, right? And your response would not only depend on the input, it might also depend on the state. So mathematically, you can represent them as, y comma output state is a function of input state and your input event. So that's how you can see a service. That's the mapping between a service to the functional world. And there's more to it. So it turns out that functional paradigm is actually really nice to model such kind of services because there is often a one-on-one correlation between the service world and a corresponding concept in functional paradigm. As I said, service can be thought of as a function, right? Event modeling. So events can be modeled using ADTs. ADTs are wonderful to model such events, and because events are immutable, but the paradigm has immutability built in. And then mostly you have stateless service. So mostly how you write a code is most of the code would be pure code, about 95% of them. And there'll be some part where you have to interact with the persistence layer, right? So functional paradigm captures the behavior of such architectures really well. OK, so this is an example of an implementation, right? It's a very simple example of, let's say, a catalog search. So how do you implement such a service? The way you implement is you define what your input pattern is. You define what your output pattern is, and often you just have to have a function that maps the two. So let's talk about an input. I'm making a search, catalog search, right? I can search by name or I can search by item number. That's my input. My output would be, I have the item in inventory, and it gives you a count of how many items I have. I don't have the item in inventory, but I can tell you a date when I would. Or I don't have the item, I don't even sell this item. So you have 3 types of output here. And then implementation would just be a function that maps the input and gives you back the output. OK, so we have talked about, this is another common pattern that we use. It's called asynchronous workflows, right? So what you have is services would place an order, right? Let's say to the stock service, and stock service wants to ship, and ship might take time. So what the stock service is going to do is it's just going to acknowledge that, right, and place an asynchronous async ship output order to shipping service. So that's an asynchronous workflow, and you have a code associated with it. OK, so we have talked about design. We have talked about implementation. Let's actually move to testing. So how do you test the request response code? For pure services, testing the code is really, really easy because I can test them exhaustively. They are very predictable. They don't depend on the environment. They don't have a state. and they can't cause any side effects, right? So you can even have there was a talk about quick check yesterday, right? And there's a commercial tool called Cubic which actually does that. And it just generates thousands and thousands of random tests on your system, right? And then it narrows down to the test that fails. So you can test these services exhaustively pure ones. Impure ones, because of the presence of external states, tend to be somewhat unpredictable. They can't be tested exhaustively. So how you architect them is try to keep majority of your code in the pure form and only minority of your code in the impure one, right? For example, you want to test your credit card billing, right? So I'm not going to test like, can I bill you $10? Can I bill you $20? Can I bill you $30? I just test once. And if I can bill you $10, I'm pretty sure I can bill you $100 also, right? So here there will be fewer number of test cases, and but the pure services I can test exhaustively. There's a similar pattern for event-driven testing, right? You have the original architecture. And if you want to test one service in isolation, what you can do is you can have a test driver and a test stub, right, implemented that way. So this service is still reading from the same message broker, and the test driver injects the events, and the test interpreter reads that events, right? So that way you can test this service in isolation. Static analysis of code. So now, one of the things we do is we do static analysis of code, and it turns out that static analysis actually is very, very efficient in detecting issues. And there's a reason for it, and reason is purity, right? So how do we do it? We have a procedure that we define a set of NT-patterns, and we have a static analyzer. Actually, Daniel there, I see him in the audience. He wrote the original part of the static analyzer. So a static analyzer parses this code and builds it into an AST. F# actually comes with an analyzer. It's called as F# compiler services. So you don't really have to have the grammar and all that defined on your own. It's built in, right? You can import it as a library. And it imports the AST. And then you have the analyzer that once you have the AST, you can walk through and detect all the patterns. And we bundle it in what we call as a SonarQube plugin. So SonarQube plugin is a software quality management platform, right? This is an open source product. You have a whole bunch of languages like C++, Java, and all those things support it. I don't know if Haskell or OCaml is, but there's nothing stopping you from writing a plugin. So anyway, so we bundle everything into SonarQube. And what SonarQube does is it has a database, it has a dashboard, we can track, we can monitor the quality of the code over time. And we have a bunch of features in work. We can provide a pre-commit testing. So pre-commit testing means you're using your ID. Generally, most of the people tend to use Visual Studio Enterprise. You can actually send your code without commit to the rules engine, and that can analyze and give you back the feedback, right? Because one common complaint you have is if your code is checked in and you detect the issues, it's like, fine, but I've already checked in, right? We have a dashboard to track violations, and in future, we would want this to be integrated in the CI/CD pipeline. The procedures apart, what happens with static analysis is because you have mostly pure functions, it's very easy to analyze the code. And the reason why it's very easy is that there are no side effects. So whatever your output would depend on, you have it in front of you, right? So static analysis actually can be very effective to detect issues in the code. Security. Another big concern is security. We have, I think, hackers trying to hack the site. I'd say almost every day we have an attack, right? So you could imagine that security is paramount. And now we made the unusual choice of using F#, which is not a mainstream language. And when you don't use mainstream language, one of the criticism is you don't have a very good ecosystem. So we don't really have a good third-party tools. I mean, there are tools that scan your .NET binaries, and they can detect issues on those .NET binaries. That's not a problem. The problem that happens is that once I know there's an issue, I can't map it back to the code, because that code, the link between code to to the binary that's not there, right? If you do it's in C#, and there are C# tools that can do that. They actually can look at your binary, detect the issue, and map it to the source code and tell you, this is where you have a problem. We can't do that. So our solution is build your own, right? So we already have the static analyzer. There's a security team that's working on it. So we are extending the static analyzer to identify the vulnerabilities and weaknesses in application code. So they have a bunch of initiatives going on, integrate security-related tooling into the pipeline. So we would ideally want that we integrate the security scanner in our pipeline. So there is no unsecure code that goes to the production, right? Work on pre-commit testing, the same as static analysis. I should be able to send my code before I commit to the repository for analysis and should know if there are any security violations there. Build and maintain tools for security analysis. The security team actually kind of does that. All right. So now that we have talked about design, we have talked about implementation, we have talked about testing, the code goes in production, what happens after that? There's a discipline called chaos engineering. So there's a textbook definition for that. Chaos engineering is the discipline of experimenting on a distributed systems, et cetera, et cetera, et cetera. You could read that. But what chaos engineering really is it's a way you can experiment on your system to build confidence and know that when you have a turbulent condition, you can actually survive that condition. For example, let's say you're running a service in 3 data centers, right? US South, US East, US West. And what happens if US West goes down? So how do you do that? Well, you can switch off all the resources you're using in US West and monitor your system. We'll see that in details, right? But essentially what it's trying to do, it's trying to experiment and make sure that when you have an actual outage, your system can survive. I think it was February or somewhere, there was a problem with AWS S3 service in the East data center, right? That went down and there was a huge outage and a lot of services went down. So chaos engineering actually is used to prevent such kind of things from happening. How it works, you define what is called as a steady state of your system, right? A state where everything should work. Typically, you would have services running in multiple data centers. You have resources, you have your VMs, disks, everything. And then you introduce chaos. So chaos is essentially an event that models a disruption. For example, what could be a disruption? Well, you have a disk failure. So what happens if you have disk failure? How do you know how your system would behave? So the chaos service, what it does is it artificially introduces an event and says, take that service down, take that disk out. So it simulates a disk failure in your production systems. It's actually done in production, right? And then you monitor your system. Ideally, when you have your service deployed, your distributed scheduler is actually monitoring your services, and if it detects that there is one VM or one disk that went down, it would try to reallocate another resource, possibly in another data center, right? And then it should direct all the traffic to that resource. So your distributed scheduler should do that. Does it do it, right? Is your service, do you have all the logic to handle such kind of disruptions? So that's what you're doing. You're monitoring the system and monitor your system and see the effect of chaos and on the system and its recovery, right? And these automated experiments actually run on your production service on a continuous basis. So you have a chaos service. Rahul, I think, is somewhere in the audience. He actually implemented much of it. And periodically, it introduces chaos like every couple of hours and then sees how you recover. So another thing we talk about is monitoring. So SLA stands for service level objectives, right? We have tight SLAs on the service. For example, every request should be responded within, let's say, 50 milliseconds. Or my site should be able to handle, let's say, 1,000 requests per second. So you have a throughput defined, right? Does it actually do that? You need to monitor, and if it's not, the appropriate parties would be informed. So how it works is that you have these services running in production, and they're sending these metrics. So New Relic is the tool we use for monitoring. These metrics go to New Relic, and Pulse service, then pulls this data and puts it in a storage. Right now, we are using an HDFS, but we'll move to a time series database called Prometheus, right? Yeah. And then we have a dashboard. Right now, it's Looker, but we're moving to Grafana, where all this data is queried. And actually, the rules to detect SLA violations are computed during the query. So you could have something like, I want to make sure that service A, the throughput is more than 1,000 requests per second. I want to make sure that for service B, every request is responded within 50 milliseconds. If it's not happening, you would immediately see on the dashboard that there's an SLA violation, and the team that handles that service, they actually get a notification, right? The pager duty stuff, and they know something is going wrong, so they can start investigating why it is happening, what's happening. Okay, so another thing you have is telemetry. When you have 1,000 services that are running and information is flowing, it's very hard to visualize how your information actually flows in this service. To solve this problem, we have what we call as X-ray platform. Actually, Gina there sitting, she implemented quite a lot of it. And what X-ray platform does is, let's say you have these services and sending these messages, right? Every time a service sends a message to another, it actually sends an event saying, service A, I have sent a message to service B, and that's event E1. Service B says, okay, I received a message from service A, that's event E2. So all these events are actually flowing in your message bus, and then they are pulled into the X-ray platform, right? From there, they are put on a table storage, and then you can search, and you have an API. And at the end, you have this dashboard, this nice little dashboard where you can visualize and gain insight on how your system is actually operating. So that's the X-ray platform. Benefits of using F#. Since this is a functional crowd, I don't really have to pitch in that much, right? If it was a C++ guy, I would have to go into details, but I'll state the obvious just for completion. Scalability, well, because predominantly your code is stateless and has immutability, you get like out-of-the-box parallelism out of it, right? So you don't have to worry about deadlocks, mutexes, and so on. Scalability is very important for a site like jet.com, because imagine the traffic we get that we have to simultaneously serve, right? So this is a huge, huge advantage. I think one of the key pitches of functional paradigm is that you can write parallel code very easily. And one of the reasons why functional paradigm in the recent years is getting a lot of attention is this, that because of Moore's law, you now actually can't make the processor more fast. So what do? You add more cores. But when you add more cores, your code should be sure that it should be very parallel. And that's easy to write in a functional language as opposed to, I don't know, Java or C++. Productivity, right? F#, like any other language, the code is very concise. So it's very easy to model the code using ADTs. So you have a lot of productivity. Your code is very concise, and you have a lot of developer productivity coming out of it. For example, if you have less code, then you have less code to maintain, so it's cheaper to maintain, right? The ramp-up time for the new developers obviously would be less because you have now less code. Code correctness, this is also something very important. You have immutability, means your code is more predictable, right? You don't have that many side effects. You have ADTs, you have exhaustive pattern matching. Exhaustive pattern matching would catch a lot of bugs at compile time as opposed to runtime. So yeah, you have code correctness. Conclusions, very few startups have scaled to the size of Jet in the same amount of time. I mean, we went, what, $0 to $3 billion in less than 2 years? I don't know. I haven't heard that many cases of that. In fact, I haven't even heard of any case like that. OK, so scalability and productivity in F#. One of the very peculiar things was our architecture that we had 2 years ago, we actually never changed it, which means it was really effective, right? You never had to change it. That's kind of unusual. Yeah, so I have about a minute remaining, so I'm open for questions. Azure is where we're using Azure heavily, right? So because our services are hosted there. So we have these VMs, Windows VM. One of the problems is because we're using .NET. .NET actually Linux VMs. Linux containers for .NET are really not that mature, right? So we use Windows VM, and services generally tends to be processes on a VM. So the VMs are in Azure. Our storage is in Azure. Our database, we use DocDB. I think that's the internal name now. Microsoft has renamed into Cosmos DB and so on. But yeah, so like I don't know. Practically everything is in Azure. So
Do you use like app fabric style approaches for distributing the services, or?
I don't think we have app fabric that I am aware of. No, we do have some. I think we are starting with a little bit of serverless computing in some parts. I think the Pulse is going to move to serverless, but I don't think we have app fabric that I know of, at least. More questions?
Time for one more? Okay, thank you, Nikhil.
Yeah, okay, so if you want to learn more, I'm here. If you want to work with us, we are hiring, so feel free to contact me.